Let's have a quick review of everything we've looked at in Unit 7, Lessons 1 through 8, which was exponentials and logarithms. First, we had to be able to recognize what was an exponential and what was a logarithm. Now, an exponential is defined as it has a constant base, which is a number, and a variable exponent, which is a letter. So some examples would be 3 to the x power, or 5 to the x minus 2 power, or 7 to the 2x plus 1 power. What it is not would be x to the second power. This is backwards. This has a variable base with a constant exponent. It would not be 3x to the 5th power. This exponent is not a variable. All right, a logarithm, that was easy. It's going to have the word log in it. If you see log, that's a logarithm. Now, there was one thing about logs. Logs all have a base. So if you don't see a base, like log 2, that's understood to be base 10. All of the other bases will have a number, but if the number's missing, that's actually a log of base 10. Then we looked at converting from exponential to log or log to exponential. So for example, this was an exponential expression. You don't see the word log in here anywhere. So we could use this formula to say, well, 6 to the x plus 1 power equals 24 can be rewritten as log. This is your base, 6. You swing over here, 24 becomes your argument, equals the x plus 1. Okay? If you started out with a logarithm, you could still convert it back to exponential form. Here was your base. Start with that. Swing over here and pick up your exponent, equals, come over here, the argument. So we could go from exponential to log or log to exponential. You just have to remember the loop. Next, we had something called the one-to-one property, and that meant, as far as exponentials go, if you had bases that matched, then you could set your exponents equal to each other 1 to 1. So this would be 2x plus 3 equals 11, and then you would just solve. Subtract 3 from each side, so you get 2x is equal to 8. Divide both sides by 2. So the answer to this one is that x is equal to 4, and you could check it. Alright, same thing over here. If your logs match and you have single logs on each side, 1 to 1, you can just take your argument and set them equal to each other. Solve whatever the resulting equation is. So we'd have x equals 5. You could also check that. And 1 to 1 was super if you had 1 to 1. But if you didn't, then you had to create that. And that's where it started getting trickier. So let's go now. We're just going to look at exponentials. I've got 2 different exponential problems here, and the bases don't match. So your goal here is, first of all, if you can, make them match. Leave it exponential and just make them match. Don't bother with logs yet. So we looked at the 2 bases and we said, is there a common root? Well, 3 is a common root for both of these. So we're not going to change the 3 to the x plus 7. 27 can be written as 3 to the 3rd power, and then you still have this out here. Now, what do you do when you have an exponent to an exponent? Well, you multiply by distributing, and we can now use our 1 to 1. Let's kind of skip a step. We're going to put x plus 7 from right here equals. Now, what happens when I distribute the 3? I get 12 minus 3x. And now I'm ready to solve the linear equation. I'm going to add 3x to each side. So I have 4x plus 7 equals 12. Then I'll subtract 7 from each side, and I'll get 4x equals 5. And then I'll divide both sides by 4. So I get x is equal to 5/4. This kind of a problem was a little bit tricky for some of you because you had sort of matching bases. It's just this was a whole number and this was a fraction. Well, we're not going to change the whole number. What we are going to do is make this into a whole number. The way you make a fraction back into a whole number is you raise it to the -1 power. Now you still have this exponent out here. Okay? So to set up your equation, you're going to have this exponent, x plus 2, equals the -1 times this exponent. -1 times 2x is -2x plus 6. Now you're ready to solve again. We're going to add 2x to each side. So you get 3x plus 2 equals 6. Subtract 2 from each side. 3x is equal to 4. Divide both sides by 3. And x is equal to 4/3. You can't be afraid of those fractions. Then we were getting ready to solve logarithm equations. And we liked doing it 1-to-1, but sometimes the logarithms weren't condensed. They weren't 1-to-1s. So we had 3 properties that would allow us to condense them so that we could use 1-to-1. We had the product property, the quotient property, and the power property. And these were easy to see. If you had 2 logs added together, then you could condense them into 1 log with a product. So log 2 of 5 plus log 2 of x was equal to log 2 of 5x. Now the difference of 2 logs was the quotient property, and it was the same except that you had a minus, therefore you made a fraction. Then your power property said if you have a number out here, then it can become an exponent. You can swing it around and let it be the exponent of your argument. So let's look at a few examples of how to use these in an equation. Here's my problem. Log of x plus 5 plus log 4 equals log 72. Notice these are all base 10 logs, but I don't have 1-to-1. I don't have 1 log over here and 1 log over here. So I need to condense these. I look for which property can I use, one of the 3. There's no exponents in front of them, so it's not power. It's got a plus sign, so I know I'm going to need the product. So I take the argument of each one, keep your log, and I multiply them together. So it's going to be x plus 5 times 4 equals log 72. Now I have a 1-to-1. I can take my 2 arguments and set them equal to each other, dropping the log. Now it's just a linear equation. Distribute this number so that you've got 4x plus 20 equals 72. Subtract 20 from each side, so you have 4x equals 52. Divide both sides by 4, and x is equal to 13. And yes, you want to fill it back in and make sure that that calculates correctly. So now let's look at this problem. Log 4 of 68 minus log 4 of 4 equals log 4, 3x plus 11. Once again, I'd love to use the 1-to-1 property, but I have more than 1 log. So if I can condense these into 1 log, I can use that. Now, I don't have a power property. Do I have a product or a quotient? Since this is a minus sign, I have a quotient. So I can rewrite this as log 4 of 68 over 4 equals log 4 of 3x plus 11. Now that I have log to log, I can make a simple equation using just the arguments, and I have this to solve. 68 divided by 4 is 17 equals 3x plus 11. Subtract 11 from each side, so I get 6 is equal to 3x. Divide both sides by 3, and x is equal to 2. Okay, now let's look at the power property. Okay, now while I do see that I have log to log, I also see that there's a number in front of the log. So that's not condensed either. But my power property lets me take any coefficient of the log, any number multiplied by it, and make that the power. So now I have log base 6 of 25 to the 1/2 power equals log base 6 of 23 minus 4x. My 1-to-1 property tells me 25 to the 1/2 is equal to 23 minus 4x. I'm ready to simplify. 25 to the 1/2 power is like the square root of 25. So this is going to be 5 equals 23 minus 4x. Subtract 23 from each side. So I get negative 4x over here and negative 18 over here. Divide both sides by negative 4. So I have 18 over 4, which simplifies to 9/2. Then towards the end, we ran into the real problem. And that was when we had a log equals a number problem, or an exponential that we couldn't find common bases and we couldn't create common bases. So first let's look at some problems, a couple of problems where it is log equals to a number. You got to be able to recognize it. I've got one logarithm and a number on the other side. This was where you could use your converting from log to exponential or exponential to log to help you solve this. So when you have log to a number, you're going to convert this to an exponential. You're going to say this is the base, so I have a 2, to the 6th power equals x minus 4. See how much simpler this is? So 2 times 2 is 4, times 2 is 8, times 2 is 16, times 2 is 32. So we've got 64 equals x minus 4. Add 4 to each side, and 68 is equal to x. So the hard part of this was converting from log to exponential, and that just used the rule. This problem I had log base 3 of 4x plus 8 minus 7 equals negative 3. I've got a log on the left and a number on the right, so this is a log equals number. Now before I can convert this to exponential form, I have to get this condensed. It's not condensed because there's a minus 7 down here. So first, let's move it over to the other side, add 7 to each side. Now I have log base 3 of 4x plus 8 equals 4. Okay? Now I'm ready to go to exponential form. 3 to the 4th power equals 4x plus 8. The conversion is just that simple once you do your condensing. So here, 3 to the 4th power is 81 equals 4x plus 8. Subtract 8 from each side, and I get 73 is equal to 4x. Divide both sides by 4. So x is equal to 73 over 4. And any problem that has a log in the original, you need to place this answer back up in here, and you need to check it to be sure that it's not extraneous, that it doesn't make a negative. So, and we're good here. Okay, so let's look at this problem now. I have 12 to the x power is equal to 8. There's no possible way for me to change this to common bases. So I have two options. I can take the log of each side, or I can convert to exponentials, which is what I'm going to do. So this converts to log base 12 of 8 equals x. Now once all this right here is all numbers, that has a value and it can be evaluated with a calculator. If you have a calculator that does nth bases, you can put it in as is and it's going to give you a decimal and that's your answer. But since I don't, I only have a calculator that will do base 10 right now, I'm going to use the change of base. And that just amounts to the log of my argument over the log base 10 of my base equals x. So now when I put that in the calculator, I'm going to have 8 log divided by 12 log equals, I get x is equal to 0.8368. And that's your answer. Okay? One more example. Okay, I've got 10 times 5 to the 3x minus 3 equals 40. I have no log in there, but I have an exponential, and I can't get common bases. So I'm going to go with converting this to logarithms. Now first I have to isolate the exponential part. So I've got to get rid of this 10. I've got to get that away from there. It's been multiplied, so to get rid of it, I'm going to divide both sides by 10. Now I have 5 to the 3x minus 3 equals 4. Converting this to logarithms, I'm going to have log base 5 of 4. Remember, you're swinging over here, and then your exponent goes over here. Now that this is all numbers, I can change this to a decimal. Once again, I don't have a calculator with an end base, so I'm going to have to divide log 4 over log 5. And I'm probably going to come over here. So let's do 4 log divided by 5 log, and I get 0.8614. So 0.8614 equals 3x minus 3. Now I know you don't like that decimal, but you can still work with it. We're going to add 3 to each side. So now I have 3.8614 equals 3x. And then I'm going to divide both sides by 3. And that's going to give me a final answer of 1.2871. Okay? Don't be scared of the decimals because you are going to get them. Alright, this was a pretty good review of everything we've gone over in lessons 1 through 8. So, I hope you're ready to quiz on this and then move on to the next topic. See you later. Bye.